We have a big task in front of us. It's an impossible task, which is compute the rank of an elliptic curve. So we have to get started. Before I start, so those who are interested in working, or they are working in the projects that I suggested, I have to go today, right after this class. I'm going back home to see my kids, and I'll be back tomorrow morning. But Mike and Bobby are going to be here at 8 p.m. This room, or maybe the other one if Keith is here still. But at 8 p.m., go find Mike and Bobby. I want to make sure you all know each other. Those who are working on this, are interested in this, just share your email addresses, just get in touch, just to see if you want to collaborate, you can talk to each other. So, last time, we were talking about this elliptic curve, and I told you, we haven't proved this, that this elliptic curve has rank 3. This is 5077A1 in the Cremona database. I know that one because it's the first elliptic curve by conductor that has rank 3. Okay? So this is very dear to our hearts, this elliptic curve. And these are 3 generators. We saw there are actually many integral points on this curve. For instance, that's another integral point. And the question is, well, if these are generators, that other one is like a linear combination of the first 3. What is the linear combination? So to solve this, we developed the theory of heights. Why heights? Why do we think that that's going to help? If you, yes?
Can I just ask you, in this special case, how do we know if it is going for it?
How? Oh, I didn't prove it. We could use the Nagel-Lutz theorem. We could do something to prove it. I didn't do it, but it is torsion free. Okay. The Nagel-Lutz doesn't apply to that model directly, but you can change the model so it's of the short Weierstrass form, and then work there and check that there is no torsion. There are other ways to do it as well, but this has no torsion. So I was going to say, why heights? Why would you think that that's going to help? Well, if you remember when we were playing around with the multiples of p, that was 3, 5 in the elliptic curve y squared equals x cubed minus 2. Did you notice that as I did multiples of that point of infinite order, the coefficients, first it became rational numbers, and then it started to blow up in the number of digits. Okay? So that tells me that large multiples of one point are going to have, in general, more and more digits in numerator and denominator. Okay? This very vague statement is actually can be made precise, and it's a theorem of Siegel that allowed him to prove that there are only finitely many integral points on any given elliptic curve. But that, generically, that's what happens. When you have a point of infinite order, you take multiples, it starts to get bigger and bigger. So what our hope is that if we add points of small height, we're going to get other points of larger height. This is not, and by height I mean the number of digits that I have to express my number. Okay? So this is 0, that's as low as you can go. This is bigger than that one because I have a 3 and a 1, and there's a 1 and a 0, there's a 2 and a 0, and a 3 and a 1 is not very compelling evidence there. But that's also what happens. If you add 2 points, you get something of higher height. So we're hoping that using height somehow, that's going to unlock the secrets of how addition works. And it does. So let's define heights as follows. First, I want the height of a rational number. So if I have a rational in lowest terms, then the naive logarithmic height let's call the naive logarithmic height of my rational number is the log of the max. Since I'm taking logs, I'm going to take absolute values of numerator and denominator. Okay? And then if I have a point on an elliptic curve, I'm going to define and P as coordinates x, y, or x naught, y naught. Then my naive logarithmic height is going to be that applied to the x coordinate of my point. So it is h of the x coordinate. Okay? That gives you an idea of how big a point is or how small a point is. So that naive height tells me that the height of this point is log of 1. The height of this point is log of 2. The height of this point is log of 3. Okay? All right. But that, it turns out that that is, it gives you some like rough idea, but there is some constants, there is some like error that happens, and some formula that we want, we don't have it exactly. And I'm not going to tell you exactly why this is the case, but there's such a thing as something called the canonical height of an elliptic curve, and this one is defined as a limit of naive heights. It's a half of the limit as n goes to infinity of the height of that multiple of p to the n p divided by, that's going to be very big, so I have to divide it by some normalization factor, divided by 4 to the n, and that this is this height, I think it's the Néron-Cade height. This converges and has some very nice properties that I'm going to tell you. So what are these very nice properties? These are listed in the book in 2.73. If you have a point on an elliptic curve, then what happens if I do the height of m times p? It turns out that the height, the naive height of m times p is roughly m squared times the height of p, but in the canonical one it's exactly the same. Okay, so that's why I like this canonical height better. And this is what, if you do in Magma and Sage, if you ask for height, you will you might actually have to ask for canonical height, but you can calculate this very quickly. Okay, what else? Something I really like also is that the height of P is always positive, and it is 0 if and only if. When do you want it to be 0? At the origin. Yes, but we're trying to calculate ranks. What should the torsion points have for height? Yeah, I don't want them. I don't want them to be in the way. So I actually want this to happen if P is torsion. Okay. And last, I don't know if you're going to be very impressed by this or not. You should be. That happens. You know what that is? Where does that come from? You've seen something like that before. So this is called something that, this is called a parallelogram law. That tells me that this is actually a quadratic form, and out of this quadratic form I can create bilinear pairings. So once you see that, you say, bilinear pairing. So we create a bilinear pairing out of this. And you get your name attached to it. This is the Néron-Cade pairing. Is defined, so it's a pairing from EQ cross EQ to R defined by you always do the same. This is not something exotic. Once you have a quadratic form, you always define this pairing in the same way. So you define the pairing of P and Q by the height of P plus Q minus the height of P minus the height of Q, and that's bilinear. Okay, very good. And I'm going to define something else, the elliptic height matrix of a bunch of points. It's going to be a matrix I call H. I don't know why I always make some sort of like calligraphic H for this. No good reason. So the height matrix, elliptic height matrix, the elliptic height pairing matrix. I define it as a matrix that the coordinates are all the possible combinations of the pairing. Okay? What is this going to do for us? Well, you heard that this is a parallelogram law. This is related to something in geometry. And what this does for us is the following. I'm going to take, you give me points, and I'm going to try to embed these points so I can actually, as we said last time, addition on an elliptic curve is very opaque. I don't know how to add. But for instance, it's very easy to check linear independence over the real numbers when you're working in a real vector space, right? So what this does for us is actually take your points, and I'm going to make n vectors in Rn, and see what that spans. If those n vectors span Rn, then I'm going to have linear independence of all n vectors, and it's going to give me some parallelopipe. And this matrix, the determinant of this matrix, gives me the volume of that box. Okay? So in particular, if the determinant is non-zero, there is a volume, and these vectors are going to be linearly independent. If the volume is zero, what happens? I don't have a box, I have a side of a box. It collapses somehow. In 3D, if you have a box, you have these three. These are linearly independent. If they are linearly dependent, they span a plane, and there's not going to be, or what they span is some polygon that has no volume. It collapses, the determinant is zero. Okay? So I call this the regulator of the n-tuple of points. That is going to be the determinant of H, of the elliptic height pairing matrix. Okay? And again, I'm not proving to you these properties. You can see more information in my book, in the notes. And if you want to see it in full, then you would have to go to Silverman's book. Silverman is the expert in heights of elliptic curves. Okay, so this is corollary 2.86 in the book. So if the determinant of H is 0, and you have a vector A1 through AN that is somehow a vector of integers, these matrices are real, okay? These matrices there are real numbers in that matrix. But if somehow you have a vector that is integral in the kernel, then your points are linearly dependent, and the sum of AI times PI is equal to what? If they're linearly dependent, is it equal to 0? Oh, it's not. They are going to add up to a torsion point. Why? Because remember, our height doesn't see torsion. Okay? So at 0, height 0 means the best we can do is it's a torsion point. Torsion is fine because we can figure out what torsion subgroup is anyways. So as long as it add up to a torsion point, we're good to go. We'll figure it out from there. So where T is torsion. Okay, and conversely, if the determinant is not 0, then your points are Z linearly independent, and the rank of E is at least N. Okay? So let me see how this works in practice. So here is the elliptic curve 5077 A1. I already compiled that. It showed me the curve. I asked for E so I can see the curve. I asked for the generators of E. You don't have to do this bizarre 0.0 thing that Sage makes you do. Sage forces you to talk like a computer, but Magma is written so you talk like a mathematician to the computer, and the computer talks to you back as a mathematician. Okay? So it gives you the generators in projective. It tells you true, true, true. It's just talking to itself at that point. It might be relying on some conjecture. At some point, there are some conjectures that might be relying on even in GRH, the generalized Riemann hypothesis, to reduce the calculations on some class groups. So it really, in this case, it didn't have to. This is true. Okay, the rank is 3. Okay, so I have my generators. I'm going to call them G. And then I want to calculate the height pairing matrix of G1, actually G, of my list of generators. There is a matrix, okay, it's 3 by 3, because there are 3 elements, and those are this is the pairing of P1 with P1, then P1 with P2, P1 with P3, and so on and so forth. That's the matrix. Very good. We'll call that matrix M, and then calculate the determinant M. Excellent. The determinant is 0.417, and those many digits is correct. So it is away from 0, so I know that number is non-zero, and they are independent. Well, the rank is at least 3. That's what this is telling me. Okay. All right. So now we had another point. We called it S, and I have to tell it that it's on E, and I think it was -3 minus 1. Yes. Yes. We complain. And then what I want to know is that a new point? Is that rank 4? So what I would do now, I'm going to do a new height pairing matrix. Of G1, G2, G3, and S. See if that is okay by Magma. Yes, it is okay with Magma. And then let's calculate the determinant of M2, you see, it's minus 3.52 times 10 to the minus 31. That's really close to 0. So I'm guessing this is actually 0. So if that's 0, then there should be a kernel in M2. And that's so. It says that kernel is within a vector space of degree 4, yes. It's of dimension 1. So there is something in the kernel. And here's a basis. It says is minus 0 point, like this real number, times something that's 10 to the minus 29 that looks like 0 to me. Then the same number, basically, and then the same number again, basically. Okay? So I'm going to take that basis. The basis of this kernel has one element, and I'm going to divide it by this number here, the minus sign. Okay, let's see what that is. Well, it's telling me that minus 1, comma 0, comma minus 1, comma minus 1, it's basically in the kernel. It looks like it's in the kernel. Okay? It is not approved because there is some like digits. Maybe it's really close to being in the kernel, but it's not in the kernel. But it doesn't matter. At this point, I have a good guess of what combination might be true. So I'm good to go because now I can try addition. This is telling me that what combination of points gives me S. What this is saying is that, where was I? So I had E that was this elliptic curve. I had P, Q, R, and then I put an S. The height matrix, the determinant of this is 0. The kernel seems to include minus 1, comma, minus 1, comma, sure. This PQR and S, this PQR, I think have changed with magma. So we'll have to make sure what those are. But I think it's telling me that it is in the kernel, right? So what that says then is that minus P minus R minus S is torsion. Okay? This is what it suggests. So let's try to see, first of all, what is G1, G2, and G3. Those points, so it's a little bit different from what we said, but S is not one of those. And what it's saying is that minus G1, minus G3, and minus S, that is a torsion point. Is that? I divide it by this number. So this number, what did the kernel change on me?
Why do you divide by that number?
To get a sense of actual integer, the kernel changed.
Probably swap the order of the generators.
What is it?
Probably swap the order of the generators.
Yeah, it calculated again. It did something else. It's fixed generators. Okay, it's called. What were my P, Q, and R? Let's say P was 1,0. Q was 2,0. And R minus 3. And then I'm going to do the height matrix of P, Q, R, and S. Let's see what that looks like. P, Q, R, S. Yes, so the determinant, the basis of the kernel divided by that number is still there somehow. And it's giving me now minus 1, minus 1, 0, 1. Okay? So now this is telling me with the PQR that we had originally in the example, that minus 1, 0, 1 is in the kernel. So that's telling me that S is P plus Q up to torsion. Okay, so I'm going to do, let's see if P plus Q, what that is. That should be hopefully S. Okay, so I figured out then, so this tells me is that minus P minus Q plus S is torsion, but there is no torsion here other than O, so it has to be O. And that tells me then that P plus Q is S. So that minus 3 minus 1 is P plus Q. Okay? And that you can read off the kernel of your regulators. This construction of a regulator is something that is commonplace in number theory. There's regulators in number fields. There's regulators all over the place. And in all cases, what's happening is that you have some algebraic structure and you want to check some linear independence, and you embed it somehow into Rn and then take a volume. So you should always think of the regulator as the volume of some parallelopipe somewhere. Okay? Okay, now I lost my place here. Okay, so any questions about this? So how this tells me if you give me points, I can check if they're linearly independent. You still don't know how to find the points in the first place, but maybe what I can say is something like, okay, this elliptic curve, the rank is at least 3. Is the rank 3? What do I need for that? I need an upper bound on the rank. Are there upper bounds on the rank? There are some. In the general case, an elliptic curve like this one, the bounds are pretty hard to come by anyway. But there are some cases where there are bounds on the rank, so I just want to give you at least one such case. So for instance, if you have an elliptic curve that has 2 torsion points, then you can write it like this, because if there's a 2 torsion point, there is a 0 on the cubic polynomial in X, and you can translate so that X coordinate is 0, and you can write it in this form. Okay? And let omega n, little omega, the number of distinct prime divisors of n, then the rank of the elliptic curve is always less or equal to little omega of a squared minus 4b plus little omega of b minus 1. And you can ask yourself, well, how good is that bound? And I did ask myself that question. I wrote a paper a while ago about it, and it seems it's I found elliptic curves, I think, up to rank 12 where that bound is sharp. But in any case, you can use it, and it actually gives you some good information. For instance, you can ask yourself, are there 3 consecutive numbers that their product is a square? Are there 3 consecutive numbers whose product is a square? It's a perfect square. You're saying no, but I say yes. Yes, 0, 1, and 2. right? It's right there. 0 and 0, it works. So are there more? Are there interesting ones? Well, let's see. This is x cubed plus 3x squared plus 2x. It's an elliptic curve. So I can try to figure out what's happening. I can try to calculate the torsion subgroup and the rank. You can use Nagel-Lutz and check for yourselves that the torsion is just 2 torsions. There are 4 points of torsion, which is the 3 that appear here, plus the 1 at infinity. And the rank, using that bound, should be given by this formula. What is that? That is the number of prime divisors of, where am I? 9 minus 8, that's 1, plus the number of prime divisors of 2 minus 1. There are no prime divisors of 1, this is 0, plus 1 minus 1, that's 0. So the rank is 0. So all the torsion points are O and 0, 0, minus 1, 0, and minus 2, 0. So the only triples of numbers that multiply to a square are 0, 1, 2, minus 1, 0, 1, and minus 2, minus 1, and 0. And that's it. Okay, so how do you find the rank? How do you find points when you don't have any? So what we do is there's a variety of methods, but they all have a common thread that they are inspired by the method of descent inaugurated by Fermat himself. He used that to prove the case of n equals 4 of his most famous theorem. And so what is the idea? How are we going to find points? There are elliptic curves where we don't know if there are points because the height is too high of the points, of the would-be points. The height might be too high. So what we want is to look elsewhere for points where the height is smaller. So I have a better chance of finding those points. So you have your elliptic curve where I run a search and I can't find my points. So what we're going to do is we're going to define a number of covering spaces where there are maps. So there is some covering spaces. These are called